Good morning, everyone. I'm Zeno Kova, and this was work done with my colleagues here, John, Corey, and Sam. So a little bit about us. We're from the MITRE Corporation. We're trusted computing researchers. Our focus is figuring out how we can make security software that isn't crap and doesn't just, have attacker lie to you and give you a false sense of security. Unfortunately, basically everything out there right now is crap. So, MITRE itself, if you probably haven't heard of us because we're a not-for-profit, we don't make commercial products and things like that. We're a research and development center, works for the US government, so basically it's supposed to be a neutral entity that's giving advice to the government as opposed to being a for-profit contractor, which is always giving advice in their own best interest. So if you've heard of MITRE, it would only be for things probably like CVE, STIX, TAXI, some standards like that. But even then, you probably don't think MITRE CVE, it's just CVE. And MITRE's been around for quite a while, since back in the ARPANET days. So we've been doing a lot of talks over the last year where we've been sort of tearing BIOS apart. We've been showing that, as you would expect, when people don't understand and don't look at this technology, it's riddled with holes. So throughout the last year, as we've been describing exploitable memory conditions in the BIOS, as we've been describing the fact that most BIOSes are just straight up misconfigured, so the BIOS vendor does not even set the access control bit so anyone can come along and write to it. We've been basically saying that modern UEFI BIOSes are sort of a double-edged sword because they help us as defenders, they help us understand the system much more than was the case with legacy BIOSes. But also at the same time, this helps an attacker understand it, and an attacker can reverse engineer it, get to the exact place that they need to compromise much easier. So this talk is basically going to be a justification of that. We're going to go through UEFI a bit. We're going to say, okay, right here, that's good for us as defenders. Right there, that's bad for us as defenders. And so that's what this talk is about. Also, we've put out tools like Copernicus, which was sort of the first tool that you could use to actually go out and evaluate your BIOS, find out whether you're vulnerable, dump the BIOS, try to integrity check it, that kind of thing. And so this will give you a little bit more context for if you use Copernicus, and we have Copernicus has a script along with it where you can integrity check. You can say, here's a clean copy of the BIOS that I've maybe extracted from a BIOS update. Here's my BIOS. Do they differ? If so, yes. Well, then how do I understand that? And so that's the other thing that is the point of this talk. So we put a tool out there, and it's all good and well for us to put a tool out there that says, hey, look, you can now integrity check your BIOS. But the reality is that if you find an integrity violation or a suspected integrity violation, you're probably not going to know how to evaluate that and find out whether it's a false positive. So this is trying to give you a little bit more context about that reality. It takes much more than a single hour's worth of discussion to understand it, but we're always willing to check to find out whether we have false positives inherent in our tool. So if you find something that's wrong and you don't understand it, you can let us know. Alternatively, we have a full 2 days worth of training on this where basically we explain, okay, here's how you analyze the BIOS to understand, here's where the change was made, and understand it better. So this is basically a whirlwind tour of that. So BIOS, meaning legacy BIOS, is dead. Long live UEFI, right? So it should be theoretically dead because it's at least dead or dying because it should be aging out everywhere because Microsoft required anything that's going to ship that has the Windows 8 sticker on it, which is most all of your PCs. There's very few things that are shipping to be Linux specific, well, except for Macs, I suppose. Everything that ships with Windows 8 requires UEFI secure boot, right? And you're probably, maybe if you're at this talk, you're maybe familiar with some of the controversy around whether secure boot is an evil conspiracy to destroy Linux and lock you out of your machine. I don't think it is, but you can have that opinion if you want. So theoretically, legacy BIOS should be going away because basically everything, all the vendors are incentivized that they have to have UEFI, they have to have secure boot in order to actually ship their systems for Windows 8 these days. But in reality, there's elements of this which will never die. So at the very beginning of UEFI, I'll show the whole obligatory diagram here in a little bit, but at the very beginning of UEFI, it looks exactly the same as BIOS. It's hand-coded assembly that's specific to the hardware, and it's required to, initialize the hardware as fast as possible. Later on, once you get past that stage, then you can build up your nice abstraction layers and you can have all the niceties of UEFI. But But if you have a change that occurs sort of, there'll be one file that typically that'll be called the sec core, the security core. That's the hand-coded assembly thing. So what I'm saying here is if you go out and use Copernicus and you do a BIOS and you find, oh, the change is in the sec core, how do I understand that? Well, unfortunately, that's a big blob of hand-coded assembly, usually using a lot of PCI accessing peripherals that you don't necessarily understand. And so unfortunately, that sort of lives on. And that's sort of the hardest chunk to analyze. But basically, we're going to talk about all the new interesting juicy bits here. So UEFI and legacy BIOS basically share two common traits. So the entry vector, meaning the very first CPU instruction that the CPU ever consumes, that's going to be at the same place on the flash chip. So the way the hardware initializes at reset, it always maps to address FFFFFF0. So 4 gigabytes minus 16, that's always the memory address where the CPU is trying to access, and the memory hardware at reset is redirecting that memory access to the SPI flash chip. So little flash chip down on the SPI bus. So they all start from the same place, and the initial goal and the overall goal is really, it's all about initializing the hardware. It's plumbing, it's getting you to a state where you can pass off to a bootloader, pass off to an operating system hypervisor, try to get everything initialized so you can have, keyboard input, video output. The big difference though, is that legacy BIOS, it was this big giant proprietary blob of stuff that did that plus a whole bunch of other things. UEFI is much nicer because it's now documented. We have a spec, we can understand what the code's trying to do in trying to understand it behaving in accordance with that spec. So also the UEFI has a reference implementation which is open source and out available. And so basically there's a single reference implementation which Intel puts out there and says, hey guys, this is how you're basically supposed to build something that conforms to the UEFI spec. And then the AMIs, Phoenix, and insides of the world, they go customize that, add their value add so that they can try to get other people to buy it, because if they didn't add anything to it, then people would just start from the reference implementation, right? So they add all the GUI niceties and that kind of stuff, and they sell it to the Dells, HPs, Lenovo's of the world. Then the Dells, HPs, and Lenovo's of the world may go customize it further. But there's some core initial open source thing that you can evaluate. We at Black Hat USA this year, we showed where Corey went and spent a couple of weeks looking at the open source reference implementation, and within a couple of weeks, he was able to find 2 exploitable memory conditions, which then, as I was saying, these propagate out to all those other BIOSes. So the point is, we can evaluate the security much more readily than we could with legacy BIOSes. So I've been using the term, but I'll expand it now. UEFI stands for Unified Extensible Firmware Interface. It was something that originally Intel made when they were trying to get rid of legacy support, and we're all to blame for x86 still having, legacy 30 years worth of cruft in it. Intel tried to make Itanium a non-backwards compatible 64-bit architecture, and everyone said, nah, don't want it, want all my existing applications to run. So now we have, 64-bit legacy cruft. Intel made this UEFI spec when they were trying to make the Itanium BIOS, and they recognized, look, we can't do all of the legacy stuff. We don't want to do all the legacy stuff that we've had to do for 30 years on the x86 architecture. Let's build up something that's a little nicer, a little more generic. And they were trying to have something that would work for x86 as well as Itanium. And really it can work for, sort of any architecture. But that was originally EFI. It became UEFI when they finally got buy-in from everybody, and it was no longer just Intel doing it, but they had the UEFI forum, which was a bunch of other companies that bought in and started doing things with it. So now, although there is this nice pure UEFI world, a lot of the machines that probably you have, unless you've bought in the last couple of years, they often have this thing built in, and there's this backwards compatibility mechanism called the compatibility support module. And what this is that basically the overall system is UEFI, but then there's this big blob of legacy BIOS in there, so that you can basically just run everything without having to change everything. So CSM is a sort of backwards compatibility. It's mostly going away at this point. Like if you buy anything new, it hopefully shouldn't be using CSM. It should be sort of pure UEFI. But that's always still a cause for concern for security problems. But The one really interesting property of UEFI for attackers is that it's getting really, really big. So, and actually I don't think I mentioned it anywhere else, so I'll mention it here. It's also written in high-level languages. It's written in C. I don't think they support C++, but you've got C code building up this reference implementation that is sort of getting giant. It's 8, 12, 16 megabytes on a given flash chip. And so, big, high-level language code, lots of opportunities for typical buffer overflows and so forth. Now, if you're not the kind of person who enjoys reading thousands and thousands of pages of specs, we are. We like doing that. That's how we find stuff that nobody else finds. So if you don't like to do that, this is a good starting point. Vincent Zimmer from Intel has, he's integral to the UEFI effort, and he's made a book that is basically a high-level overview. But if you want to jump right in, you can go download all the specifications. So this is what we're going to sort of be working our way through today. This is, everybody who does BIOS talks these days has to put up this picture. This is Intel's sort of description of how notionally UEFI works. You start at the very beginning, security phase, and theoretically that's where security is, but in reality that's not. Then you have pre-EFI initialization, so you've got, well, I won't go through them all. We'll hit them each in turn. So there's 7 phases notionally, but in reality they're not all used. But we're going to start a little bit lower than that. And so we're going to start sort of what things look like on the hardware these days. Okay. So legacy BIOS, you had the SPI flash chip or the Intel firmware hub on things typically older than 2007. And this is basically, if you think about your computer architecture you're maybe familiar with, or you've maybe heard the term, north bridge, south bridge. So you have a CPU, you had a north bridge which handled high-speed peripherals, and then you had a south bridge which handled slow-speed peripherals. The SPI flash chip is hanging off the south bridge. Modern systems, the chunks of the north bridge have gone into the CPU and other stuff has gone into the south bridge, so now there's just sort of CPU and platform controller hub, and the flash chip hangs off the platform controller hub now. So the legacy BIOS was basically a big proprietary blob, as I was saying. Each vendor had sort of their own proprietary formats, which would typically have to be reverse engineered. And people online would reverse engineer it for various reasons, and then they'd put up tools in order to break these things apart. This is sort of, analogous to, right, this is the bad old days, and if you saw the firmware.re talk yesterday, that's still the world they live in. They've got all these proprietary, compressed and packed sort of things. And if you go back more than, 6 years, 7 years, this is what you'll still see on x86 systems. And typically they looked like a packed file, which means you had, in order to save space on the SPI flash chip, always the vendors were trying to, save pinch a fraction of a penny times millions of machines means actual money saved. So they would use the smallest possible flash chip, and they'd have a little decompression routine at the beginning. So you call into the decompression routine, and then it expands stuff out into RAM once RAM is available. That's weird. So nowadays, SPI flash chips, Intel mandates that you have certain characteristics of flash chips, like they must be able to be rewritten like 100,000 times or something like that. So they have certain requirements that they put on flash chips, and they require that they support this notion of a flash descriptor. Flash descriptor is sort of a data structure that's put at the front of the flash chip, and that then describes specific regions within the flash chip. So a gigabit Ethernet region that has sort of configuration information for gigabit Ethernet, platform data that has miscellaneous stuff, management engine, if you've heard of AMT, active management technology, maybe you heard of the talk of attacking that many years ago. That contains information there that is consumed by the management engine. And then UEFI BIOS region, there's sort of a BIOS region described by this. That's where the actual contents we care about that we want to analyze are. And so the flash descriptor can create new regions, so this will probably increase in the future. But for the time being, that's what's there. All right, I don't know why I used animations. I think I copied some previous slides and they used animations. So with what we care about here within the BIOS region, in the UEFI BIOS, it's going to be organized according to firmware volumes. So what this turns into is that we have a nice, well-defined, well-formatted firmware file system ultimately. So the spec lays out that there's quote-unquote firmware devices, which may be real or physical. The firmware devices are broken into firmware volumes, which can be nested, so you can have firmware volumes within volumes. I sometimes think of the volumes kind of like folders, and then there's going to be a whole bunch of files in those folders, and there may be a compressed folder within a folder. And oftentimes we see, we'll cover the phases in a second, but just so you know, oftentimes we'll see the folders sort of broken up, that all of the files that run in one phase of the boot are in one folder, and all of the files in another phase are in a different folder. But ultimately the base unit is a flash file. And so these flash files, it has some well-defined structure, it has well-defined, ways that we can find it, parse it. But within each file, there are then actually separate sections, and that's the part that we ultimately care about. That's the real file that we care about, because a given section will be, for instance, what's called a dependency expression, meaning like here's the other stuff that needs to load before this file loads. Or a given section will be an actual portable executable file. So, as is said right here, when we dig all the way down into this firmware file system, we find that the different sections can either be portable executable format or they can be terse executable format. So PE, if you know Windows, PE is basically Windows executable format, Microsoft's format. And then TE is the exact same thing, but they basically just collapse down the headers. So, here's the thing where both the good guy and the bad guy say, hey, how interesting, my BIOS uses quote-unquote Windows executables, right? I know how to analyze those. So I as a defender know how to analyze those if someone modifies them, and I as an attacker know how to break them apart, analyze them in IDA, and figure out where I need to insert my hooks or what have you. So there's basically three options that you have right now for firmware file system parsing. There's EFI Pwn, which is the thing that we currently use within Copernicus's extra scripts, but because this was something that was just sort of put out by a student, it was the first one, and it was, at the time that we started doing this, it was what was available. We didn't want to make our own. We certainly could have, but why not use someone else's code that's out there? But this is not maintained over time, and we've been sort of getting tired of hacking in additional support and fixes and so forth. So the other tools are UEFI tool, which also, this is a nice GUI thing that we'll see in a second here. And then there's a thing called UEFI extract, which will basically pull out all of the files, dump them off to your file system. And then there's UEFI firmware parser, which was another thing that is being maintained and being actively updated. And we'll see that a little bit later too. So we'll come back to this later as we determine whether we have enough time. But this is basically what you'd see in UEFI tool. You go, you dump a firmware file in here, something Copernicus dumps out, something you extract from a BIOS update file. You dump it in here, it'll slice it apart and say, here's the different regions that the flash descriptor defines. And then within the BIOS region, you can actually expand that out and you can see all the individual files. So like I said, we'll come back to that. But for now, this is just to say, okay, there's an easy way to start digging information out of these files. So, from both the attackers and defender's perspective, right, standardization is a good thing, right? So standardization helps the attacker find that, okay, well, I can now analyze all BIOSes for all vendors in a nice, easy way. And that also helps us, though, as a defender, right? So we can now have generic integrity checking software that breaks everything apart the same way and gives us more semantically meaningful information about, okay, well, it wasn't, I'm not just telling you, hey, there's 3 bytes different at offset 2457. I tell you that within the .text section of the portable executable file that's called, PEI initialized memory, that is where we find, a 3-byte change and, hey, it looks like a jump instruction. Right, so it works for and against us to have this standardization, right? But the real question is, who tends to move faster, attackers or defenders, right? There. So the sec phase or security phase is the very first notional phase. This is a binary blob of hardware-specific code. Needs to get the system up and running as fast as possible and just pass off to the PI phase. Now notionally, you can see here it says pre-verifier. Hopefully that's somewhat readable. Pre-verifier should theoretically be the core root of trust for measurement. There should be an ability from within this code to measure the rest of your BIOS and confirm, well, you're not even bothering with confirm, just get a measurement and store it off to some trustworthy location like a TPM so that you can actually say something about, is this code look like I expect it to look? In reality, last year at Black Hat, we did a talk talking about how these static roots of trust for measurement are sort of fundamentally broken. But there's additional technology that's going to be coming into place soon that will improve that. But notionally, they had this idea of the sec phase is where the most important security stuff goes down. Obviously, if you compromise the system this early, if you compromise at the very beginning, if you can modify the very first instruction that the CPU ever executes, then you are in the most trustworthy position. You can modify, manipulate, and make the system lie for everything else that happens thereafter. But the security phase, it executes from flash chip, so it actually is like living in the flash chip. There is no RAM initialized, and then it moves along. Yeah, and that's what I thought I had it somewhere. The security phase is a misnomer. In reality, all the security critical things, the verification of digital signatures, the measurement of the BIOS, on actual real platforms, they don't actually match that. They do it much later. And that means that an attacker coming in earlier will always win. Yeah, so that's where it should go, but that's, it's a good, UEFI is another one of many great examples of how things can be architecturally correct and implementation incorrect, right? So it's all good to say, oh, well, I see that they're doing the right thing in the architecture, it must be okay, right? That's why we have to go in and actually evaluate things. So a miscellaneous point, which I don't want to dwell on too long, is just that when you're booting up the system, there's multiple paths that the system will take depending on the sleep state it was in. So if you just reboot a system, you're coming from an off state and you're going to go in. An important point, which will, the only reason I mention this is that, I mention it for the reason described here, is that there's different, when you want to explore the potential for vulnerabilities on the BIOS, you have to explore that there's different code paths that it'll go down depending on whether you just went to sleep and woke up, or you went to hibernate and you woke up, or you're coming from a cold boot. And so these sleep states, they're ACPI sleep states, but as I said, they go to different code paths. So what we've found and what we'll be talking about later in the year, we've got a whole bunch of vulnerabilities we've already described. We've got a whole bunch of vulnerabilities that are still in for disclosure. We're having the vendors fix them. We found situations where you may have a system and Copernicus may say, oh, this system is currently locked, it's configured correctly, it's protected, that's good. But then you put the system to sleep and you wake the system up and the BIOS does not do the right thing upon wake, and it doesn't lock things down that got unset as a consequence of sleep. And that means then, all it takes is one sleep and one wake and you're back to a vulnerable system, which on laptops is, pretty guaranteed to happen pretty quickly, right? So we'll be talking about that later in the year. And so actually there was a specific issue in Dell machines that they patched quite a while back, like last December. We just haven't got around to the problem is it's not a full conference talk worth of information. It's just, hey, it went to sleep, came up, it's vulnerable now. So we're adding that and combining that with some other problems to get it to be a full conference talk worth of information. So some of the type of information that the sec phase is responsible for is configuring the CPU for cache as RAM. This makes it so that even though your RAM is not actually set up yet, by the time you get into the next phase, the PEI phase, you can actually have C code executing in the PEI phase, because if you don't have a stack, if you don't have this ability to push and pop, then you can't expect that normal compiler generated code will actually work. That's why sec phase is hand-coded assembly, where they're doing their best to never try to use memory or temporary space. But once cache as RAM is initialized, then you can have compiler generated code running. And then it has to activate the main CPU and so forth. So originally, in the full version of this, we would go down like everything and talk about all this stuff. But this is just to speak to. There's a nice Intel white paper out there where they're talking about reducing platform boot times. So you may know that going along with Windows 8 Secure Boot are also requirements such as you must boot this fast. Well, if you put requirements on the vendors that they must boot fast and they must boot securely, they're probably gonna, the boot fast one is the easier one to achieve at the expense of the boot securely. So So this is just to say that if you're interested in that kind of thing, there's a nice Intel white paper out there that you can look at for reducing boot times, and that talks through all of the. This can also be used to understand like what the BIOSes are maybe doing in each phase. You can say, well, maybe the vendor was trying to implement this, and they were, this is why the microcode update is right here. This is why the cache's RAM is right here. But ultimately, when the sec phase is done, this is where the niceties of standardization comes in. There's going to be some handoff to PEI. So it's initialized everything. It's got the sec phase's responsibilities taken care of, and it will now collect information which it'll pass to PEI. That information includes things like information about the operating environment, such as where the temporary RAM is, like how much cache's RAM has it actually initialized, location of the temporary stack, location of the boot firmware volume. So this is basically a firmware volume, as we were discussing before, on the flash chip, and it's telling you here's the offset to the firmware volume so that you can start decompressing or just pulling and parsing the information in order to boot all of the PEI phase code. And a list of, that probably shouldn't be even talked about yet. So the PEI phase, the pre-EFI phase, a lot of work goes on here, but then ultimately much more work will go on in the Dixie phase. So its job is to initialize permanent memory. So this is where you actually initialize RAM and you actually get the system into what you would think of as a normal running state. It also then, once it initializes memory, it has to pass that off to the next phase and say, here you go, next phase. You can just assume that RAM is initialized. It describes, there's a variety of handoff blocks of, again, metadata that it must pass on to the next phase. And ultimately, its job is to, once it has executed all of the PEI phase hardware initializing modules, then once everything's complete, it will go ahead and pass to the next phase. So in the PEI phase, we have this notion of a PIM, pre-EFI initialization modules. So PIMs are the types of things where now we've got portable executable files, well-defined things. On some systems they're PEs, on some systems they're TEs. But they're basically this nice modular format where different chunks of code handle initialization of different hardware. And also, very interestingly, they have a well-defined structure where they create basically APIs for each other. So they say, I am a PIM that handles, status reporting information. So I handle like writing to a console log, or I handle writing to the flash chip. I handle logging type thing. I'm going to register a PIM to PIM interface. And now anyone who wants to log stuff, they can look up my PIM to PIM interface and they can go ahead and call into me. And so although the binaries are portable executable files, they don't work the same way as like DLLs on Windows. They don't like import a DLL, that kind of thing. What they do is they have this well-defined interface, the PPIs, where you look up things that you care about. So when you're writing the code, you say, at some point I'm going to need to call into this interface that's defined in the UEFI specification for here is how I find the logging code, right? So I just do lookup logging code, I get back a pointer, and now I have a data structure that I can use to call function pointers within that code. So this is going to be sort of interesting, and an analogous thing will happen in the next phase. So there's the registration of the PPIs. There's PEI dispatcher. So this is the thing which is basically going to chew through the firmware file system. And it's going to say, okay, I see that there's a dependency expression. The dependency expression says, I can't load this module until these 5 other modules are loaded. So again, it doesn't work exactly the same way that like an import address table, import names table, that kind of stuff in Windows would work. There's these files on the firmware file system that says, here's the prereqs for this file. You, the dispatcher, must go off and pull all these things in, run them, and now you can load this. So the dispatcher has to handle the logic for that. And it handles the firmware volumes and services. So this is where there's some core services within the PEI phase, so that each PIM can have an expectation that it can find other PPIs, it can find other firmware volumes. So this again is where. So if I pick up the pace, we'll get to see at the very end where how code actually uses these sort of tables. But This is a data structure that you can assume, like if you're reverse engineering the code, you can say, I will expect that this data structure will be passed into the main function of a given PIM module. And so when I see it offsetting, when I see it doing, pointer arithmetic, and I see it going, okay, this pointer plus 32, okay, now I know that that's whatever it is, plus 32, I don't know, it'd probably be reinstall PPI. So you can start easily figuring out the semantic meaning of the code's utilization of function pointers, because what I'll tell you is that when you're looking at the code for these things, it looks very much like C++ code, and I mean that in the most annoying way. So C++ code, virtual functions, things like that, indirection calls through function pointer tables. That makes it hard to follow control flow. That makes it difficult to see, hit cross references on a given function and see everywhere that it's used. So that sort of indirection is used extremely much in all of the PEI phases. You're always going to see things referencing through these sort of function pointer tables. But at the end of the day, with some appropriate use of IDA importing of data structures, you can actually it can actually lead to making very semantically rich pseudocode. So this is how you should think of the PI phase. It starts off, you've got the dispatcher, and then it chews through all of these PIMs on the firmware file system. It pulls each of them in, executes the entry point, figures out what the dependencies are, and does this nice series. Ultimately, once it's done with all of the PIMs, then it's responsible for finding the Dixie IPL initial program loader PIM. So this is a PIM, but its only job is to kick off the next phase, the Dixie phase. So, and I'm going to skip that in the interest of time. You can go read it later. So, handoff blocks then, as the PEI dispatcher finds the Dixie IPL, its job is to take these handoff blocks, well-defined data structures, pass them into the next phase, and then the Dixie phase will know where the memory is. It'll know where the firmware volumes are, and so forth. So the Dixie phase is honestly the most interesting phase most of the time, because a lot of the stuff that goes on in the PIM phase is just hardware initialization. It's pretty rote. It's just, if you have this particular chipset, you initialize it in this way. The Dixie phase is where all of the interesting sort of secure boot things and setup of system management mode, all of the good juicy bits are here. So from a high-level view, it works in the dispatcher within Dixie works the same way as the PEI phase. So there's sort of one-to-one mappings between, they just, at a high level, the structuring of the Dixie phase and PEI phase are the same. So whereas in PEI we had PIMs, these PEI modules, in Dixie phase they're called Dixie drivers. PEI dispatcher is just like the Dixie dispatcher. It just goes through the firmware file system and finds all the things and loads them in an order appropriate according to the dependency expressions. The PPIs, these PIM to PIM interfaces, a way that you register for other code to be able to find you and execute and invoke your code. That's called a protocol in the Dixie phase. So if we talk about a Dixie protocol, we're saying here's some code that I've registered and I let people look it up and I let people call it. And then just like the sec core gave data to PEI, PEI gives this well-defined data, the hobs, to the Dixie phase. So if you take that exact picture and you fill in Dixie for PIM and Dixie IPL for boot phase, it'll be the exact same thing. So I was saying that basically there's all these function pointer tables which are used, and I guess I didn't highlight the red ones last time, but the ones that we sort of care about from a security perspective, and honestly that's probably not that visible on there either, the ones we care about are things like trust and process firmware volume. So there's this data structure, the Dixie services data structure. It's going to be passed into the main of the Dixie phase code, and it's going to then, that phase is going to use these function pointers in order to call these sort of core Dixie services. The trust phase, well, so the process firmware volume, that's basically, if I'm a Dixie driver, I'm going to call process firmware volume in order to find another firmware volume, in order to find some other code that I want to load potentially. And that processing potentially, this is just stuff which is implemented by the Dixie core. That processing, anytime there's parsing, there's potential for exploitable memory conditions, parsing mishaps. And so that's one obvious place where vulnerabilities could happen. These other things, they're just I/O space, memory space, access type of things. And then trust is kind of interesting because it basically says, I'm going to mark this firmware volume's worth of information. I'm going to mark this executable that I'm loading as trustworthy, and then I can go ahead and run that. So fundamentally, if I'm a UEFI rootkit, I can just go ahead and hook into something and call trust on it, and then it's going to just bypass any other additional checks. It's going to bypass signature checks and so forth. In addition to the Dixie services table, there's going to be a whole lot of function pointers for use within this phase. There's the Dixie services table, there's the boot services table. This has then the install protocol interface, reinstall protocol interface, uninstall, handle protocol. These are the things where if I want to say that someone else should be able to call into my code, I will call install protocol interface. And then someone else will, where is it? There should be a lookup, locate protocol somewhere. I don't think I highlighted it, but then there's register notify. So register notify is interesting because you can say, I know that I'm going to need this protocol, and call me back whenever you get around to loading a Dixie driver that actually implements that. So you can have callbacks where later on it invokes your code once the prerequisite code is actually started. Load image and start image, those are basically image in this context is now portable executable files. This is loading actual executable code. So that's starting up that, and open protocol is call into something else. There it is, locate protocol. So 3 pages worth of function pointers just in the boot services table, but some of them more interesting than others. And finally, then there's some even more function pointers that are available, but this one is especially interesting because, I don't know why that was animated again. Runtime services table, it's something that the Dixie phase has access to, but this is something that persists into the runtime of the operating system. So it's set up during the Dixie phase. There's going to be some core Dixie driver that handles the behind the scenes code for each of these function pointers. But whereas those other tables, boot services table and Dixie services table, those things are sort of going to go away once you get past the bootloader. They're sort of for BIOS use only, and then they're going to be recycled. Their memory is going to be recycled when we get past the bootloader. The runtime services table sort of sticks around forever, and this is meant to be sort of an interface from which the operating system can call into code that was provided to it by the firmware. And so this is a potential place where sort of less privileged code, an operating system, can pass information for processing to more privileged code, the firmware. And we call the firmware more privileged because it sets up things like system management mode, which can exist behind the scenes forever. So at Black Hat this year, we had shown how from Windows 8, it exposes this runtime services. So although it's called something else, really you're calling into an API, which is really just a front end to set variable and update capsule. So utilizing these, the ability to call into these function pointers, we can sort of stage information which the BIOS is going to consume and process upon next boot. And we'd found these exploitable conditions where we could create this update capsule that has to do with BIOS updates, essentially. So we can create a fake BIOS update full of non-signed but memory corrupting information, create a fake update, reboot the system. The BIOS says, oh, I see that you've staged a BIOS update for me. I think I'll go ahead and parse that. And then ultimately in the process of parsing that, it'll choke and die, and the attacker will gain code execution at the very beginning of the system boot. The set virtual address map is sort of, I don't know, it's interesting for people like me who deal with memory management and things like that. It's basically like the runtime services table is sort of left around, but they don't really have relocations per se in the same way that normal portable executables have relocations in Windows. So when you first want to access the runtime services table from an operating system, you just sort of scan through memory, find the table based on a signature, and then once you find it, you call into this set virtual address map, and then it's going to sort of do a relocations on wherever the BIOS stuck this in memory. You, the operating system, or you, the attacker, have mapped this into memory at some location, and you're telling the code, hey, I've mapped you into memory at this location, go fix yourself up for me so that all of your hard-coded constants are now at the right location. So, and then even beyond the exploitable update, there are other things where just the ability to access UEFI firmware variables has allowed for bypassing set variable. If you maybe heard of those cases where, they were blaming Linux at the time, but really it's a firmware problem, but they were saying, if you boot Linux on this Samsung laptop, it will brick your system, right? That was a case where basically the Linux was using the UEFI non-volatile variables in order to save logging information, and at some point it would just sort of exhaust the space available for variables, and so they were using this set variable and just filling it in with logging information, and then eventually a BIOS choked the Samsung, or eventually there was a Lenovo example as well. The BIOS just choked on too many variables, and then it just refused to boot. So in terms of relative magnitude of PIMs versus Dixie drivers, you can use these firmware parsing tools, and you can see that if there's 65 PIMs, there's 279, 78 Dixie drivers. So there's many more Dixie drivers. They're all like registering these protocols and talking amongst themselves, and implementing potentially pretty high-level things. We'll see here at the end again if I move faster. We'll see like the names on some things from which you can sort of infer that they're doing pretty high-level things. They're doing graphical things. They're doing. I don't think there's going to be a name specifically that you can call to that, but I know that HP at one point had this value add to allow you to check your Outlook mail from the BIOS. So like those splash top operating systems where they said, look, it takes 1 second to boot, and then you've got like a browser and you've got your email and everything else. Right, so that's good from sort of a usability perspective, right? You can boot to just something quick, but that means there's all that sort of code being implemented down at the BIOS level to have problems can be there. So I've already made reference to the UEFI non-volatile variables. I just hand waved over them until now because basically, in your legacy BIOSes, you would have this notion of CMOS or NVRAM, non-volatile RAM, that stored your configuration information. But that was it was a very limited amount of space that the BIOS vendors would twiddle bits there and set config information. In UEFI, you have this well-defined data structures called non-volatile variables. And these are stored actually on the flash chip. So there's going to be some amount of code on the flash chip, and then there's going to be this data, these non-volatile variables on the flash chip. And those are used for configuration information. I already spoke to that Samsung Lenovo case where theoretically just fill up the variables and you can brick the system. And then also there was these exploitable conditions in the past. So PEI may touch the variables a little bit. For instance, with this fake BIOS update, it was checking for the presence of one variable, and when it found it, then it started invoking BIOS update. But typically it's the Dixie phase and later which utilize them. So this is just to say what sort of attributes a non-volatile variable can have. It's all defined in the spec. So non-volatile, obviously, they can be volatile, but we care about the non-volatile ones. Boot services access means that it will be accessed up through boot, and it shouldn't be accessed thereafter. Runtime access, this is the one that we sort of care about a lot. This means that it's going to be accessible later on when the operating system's running from within that runtime services table. Hardware error record, not that interesting. Authenticated write access, this is something that this and the time-based authentication, these are things where it makes it much stronger than the bad old days with CMOS. With CMOS, anyone whose kernel can just go twiddle to bits once they'd reverse engineered it. With authenticated non-volatile variables, they actually have digital signatures. Well, they don't have digital signatures on them. The gatekeeper, the code which implements the reading and writing to the variables, it will make it so that you cannot write to this variable unless you have provided me a digital signature that actually is signed by the key of the platform manufacturer or signed by another key that you've added in. And so it makes it so that anything that's important can be stored in these variables and locked down so that it can't be manipulated by an attacker. And yeah, so if something's both runtime and authenticated, that's where you would put your typical security information. But if you see runtime and not authenticated, that means it's open to attacker manipulation. And so in the case of the setup variable stuff, this was something where I just said that the gatekeeper is the one who does the, you hear, okay, well, this is a signed variable, so someone has to check the digital signature. It's like, who's going to check that? Well, for most implementations, it's someone like system management mode. So when you're calling into the runtime services table, that's shunting into system management mode code, which is, protected by virtue of just being in system management mode. But then if you have a misconfigured BIOS where anyone can write to the flash chip, that means you can completely do an end run around the gatekeeper, the authenticator of these variables, and consequently you can just modify stuff however you want. And that was this Charizard attack that we'd presented earlier in the year. So amongst the interesting things about amongst the interesting non-volatile variables, the most important authenticated non-volatile variables are the keys, so the key storage. And this is sort of where the controversy with the Linux things comes from. Platform manufacturers who are shipping Windows 8 certified things, they're obviously going to have Microsoft Windows 8 key within the BIOS as one of these keys. It'll typically be the platform key. So you've got these notions of keys. There's platform key, there's key exchange key, there's signature database and forbidden database. So we'll start at the bottom. Forbidden database, this is a black list of UEFI modules which have been found to potentially have vulnerabilities, and so they can add in a blacklist and say don't ever allow that. Signature database, this is a whitelist where you can just not even have to care about keying, and you can just say I want to put a whitelist entry in for my bootloader or whatever, and then you can just boot the system. So the whole notion that you were somehow being locked out of your Linux, it was as simple as adding a whitelist key for a bootloader. You didn't even have to do that whole thing with signing with a Microsoft key or anything like that. They chose to do that because they were going for the easiest, most least painful way in order to make the system boot. So. But then, in reality, most BIOSes, they're going to give you an ability to go in and add whatever keys you want. So they could have said, oh, you're going to add a Fedora key, you're going to add a Red Hat key. But if you go back and read the articles about that, they're saying we evaluated many different ways of doing this, and we decided that just signing with Microsoft's key was the least pain for everyone. But it is absolutely possible that they could have just done it many other ways where you just manually had to, set a key, for instance. And I suppose I should say it. Well, I'll say it later. Never mind. But these keys themselves, they're authenticated variables. They're sort of written into the flash at manufacturing time. They're signed. They're marked as authenticated so that you're not supposed to be able to touch it unless you actually are doing the update with a del key. But again, if you can get around the signature requirements, you can obviously go modify that. I kind of already said that. One miscellaneous thing, although we haven't talked about it here, there are other protection mechanisms within the BIOS, things like protected range registers, where the chipset can say, this region of the flash chip is non-writable and no one should ever be able to touch it. The thing is, those other protection mechanisms can never really be applied to the UEFI non-volatile variables. The variables are always sort of going to be a little bit vulnerable, more vulnerable than the code itself, because they can't be marked as pure non-writable, because if they're a runtime access variable, they need to be rewritable on the fly. So that's just sort of an architectural thing where we can potentially get around it, and I already mentioned that. So Dixie and system management mode are best friends forever. System management mode is the most privileged execution domain on an x86 system. I wish I would have put in sort of an Intel manual picture, but just to remind people or to inform people who aren't aware of it, right? You have your typical CPU, it reboots into real mode. Real mode is your flat, no protections, DOS sort of mode. Anybody can access anything. Eventually an operating system or bootloader moves you into protected mode. Protected mode gives you your ring 0, your ring 3, gives you paging and things like that. Off to the side, there's this notion of system management mode, and it's the BIOS's responsibility to put code into a location that's called system management RAM, and then it's going to lock down that RAM so that basically SMM code can execute without interference from an operating system, and it sort of executes upon system management interrupts. So Dixie phase is the one who's responsible for actually instantiating SMM code. SMM code, I should have put it on here, I should have put a nice little evil attacker. SMM is almost always to the attacker's benefit over the defender's benefit, because it's an architectural place. The way it was put is Intel created SMM to allow for confidentiality and integrity, and those sound like good things that are nice, right? But unfortunately, it's not your confidentiality and integrity, it's the platform manufacturer's confidentiality and integrity. So just the way it works is the platform manufacturer, the BIOS maker, they put code in there, and then that code gets locked down, gets to run in the background forever, and you don't get to ever inspect it at runtime. So SMM is sort of the ultimate place to hide. If you look at our Black Hat USA talk from earlier in the year, we showed, we just said, here's a proof of concept, here's a flag in the ground, here's an SMM attacker, here's what they could look like, and if security vendors can't find this, then they shouldn't pretend to be giving us security. So SMM is sort of it's in the Dixie phase, so if you break into the system at the Dixie phase or before, then you should be able to compromise SMM, have this code that's invisible, running in the background, capable of subverting everything forever. All right, boot device selection phase. This is just a sort of very short sort of intermediate phase. It's going to be a single Dixie file, so when Dixie passes off to the BDS phase, it's going to be some file that handles a selection of, are we going to boot from a CD, or are we going to boot from a hard drive, bootloader, that kind of thing. And it decides where you're going to go from next. Now, it should be sort of, if this is a boot manager, if this is determining where we're going to boot, it should be clear that basically by this time of boot, file system access and potentially network access, if you're going to do a network boot, are all set up. And so the Dixie phase has created all of these nice interfaces, these abilities, all these abstraction layers for the BDS. Doesn't have to know how to access FAT versus NT or NTFS or anything else. This UEFI interface gets set up, and it allows you to just call into APIs which handle all of the abstraction for you, and that's why there's so many Dixie drivers. They're supposed to set everything up for eventually the bootloader. And so the one thing I want to highlight on this picture here is that when we talk about UEFI, and it's sort of hidden in this picture, the UEFI interface is basically a thing for the bootloader and this other stuff in the next phase. This is the interface by which stuff can call in and have all these abstractions pre-made for it. And the runtime interface is down here as well, and that will persist forever, whereas the UEFI interface will go away eventually. Skip. So transient load phase, this is kind of interesting because you can have transient OS absent applications running. And so this is one thing that potentially works well for us as a security, as a defender. You can say, okay, well, I'm going to boot my system and I'm going to start up an application that actually checks, reads into the UEFI interface, does evaluations of whether or not those system calls are hooked and that kind of thing. But even at this phase, it denies unsigned applications. So if you want to do this, you either have to whitelist your applications or you have to sign it with one of these platform keys. And so there had been, extremely lame talks about, oh, look at me, I made a UEFI bootkit, except one of the main reasons UEFI is even being used is because of secure boot. It stops things that are unsigned. Yes, you can make a bootkit if the signature verification is off, but that sort of is stupid. So there had been various talks. There had been typical bootkits. There had been bootkits running from UEFI, from option ROMs and things like that. And if this is the general point of a bootkit, we know that there's a standard methodology for bootkits. They start early in the system, but really they can't just live there. They have to sort of bounce their way down into operating systems, corrupt data structures, turn off security, that kind of thing. So that's the sort of standard methodology. And this transient application, OS absent application, gives us this ability that we can run security tools early, pre-boot, and evaluate and assess something about the UEFI interface as well as the operating system. Now, this doesn't help us at all detect SMM attackers and things like that, but it does help us detect trivial, typical function pointer hooking, your typical rootkit type techniques. All right, then there's the runtime phase, and basically at some point when the bootloader is done, it's going to call exit boot services. That's an API within the UEFI spec. You call that API and it basically says, okay, anything that is not marked as runtime accessible memory will now be recycled, thrown away, and only the runtime interface should maintain. Then there's an afterlife phase, which in reality is one of those things where they specify it. They say maybe someone will use this someday, but as far as we know right now, nothing's using it. Notionally, you could think of it like the system's going to go down and you'd like to have a graceful way to maybe clean up some information that the BIOS stored in memory. All right, so where does secure boot come into all of this? So I just whip through all those phases quick. So secure boot's job is to basically make it so that, why did Microsoft require secure boot, right? Well, because Microsoft is having their lunch eaten by having bootkits, which can turn off all the security, right? It should be obvious that like there's no architectural way that you can protect any operating system, Windows or Linux or Mac, unless you have some security pre-bootloader. Because if the bootloader is accessible, the bootloader can be overwritten, it can compromise anything in the operating system, right? So what they're trying to do is pull back the security to earlier, make it so that if you want to attack it, you have to go as deep as possible. And certainly we know that most attackers don't do that. So the point is to pull the signature checking back so that you can say, this is the bootloader that I expected to run, and this is the firmware that I expected to run. And so I'm going to reuse some Intel groups slides because I think they showed it the best way. So the first thing is that firmware signing, it's evaluated typically, unfortunately, it's evaluated not sort of at every boot, not by hardware, not in sort of an architecturally secure way. It's evaluated at the time that you're about to write something to the flash chip. So maybe the existing BIOS checks it, or heaven forbid, just an application within the operating system checks it. Some vendors had done that at some point. But the idea would be the existing BIOS is there. It was written. It was a known clean version at the time that it left the plant. The BIOS vendor checks the digital signature on an update that's about to be written to the flash chip, and then it just slaps the entire thing onto the flash chip. Now the thing here is, if you can get onto the flash chip, because there will be no subsequent checks, that means you can always subvert the secure boot right from the very beginning, because it doesn't check it every time. It just checks it at the time that it's written. So, the angel here would say, well, that's a necessary performance optimization, that kind of thing, but it is what it is. So then, once you have this notionally just presumed trusted contents of the flash chip, that code can then actually check if you have other applications, other bootloaders, other option ROMs that are signed. It can check the digital signatures on those each time so that these things coming in from less trustworthy sources can actually be evaluated to determine whether or not they're manipulated. And then ultimately, Windows 8 Secure Boot nests on top of UEFI, and they then start, checking their operating system loader itself. So the UEFI bootloader is checked by sort of the BIOS itself, but then the bootloader has been checked, it's been confirmed to be signed, and then it can pass to an operating system specific bootloader. All right, so the good thing about Secure Boot is that, as I said, it's sort of the only way that you have to pull the security checks back to an earlier phase in order to not have the operating systems be just architecturally subvertible. But this works in an attacker's benefit as well, because you're going to assume that the BIOS is secure, and then you're going to say, well, Secure Boot's protecting me, and then I don't need to go check my BIOS, right? So looks like I'm running a little late, but fast enough that I can show you something real here. So now we're going to pull back, look at some of the type of information that's put on the firmware file system, and give you a sense for, now that we know these phases and what's in them, that kind of thing. Now we can see what kind of stuff is all mixed together here in the flash chip. BIOS analysis for the detection of advanced system subversion, that's our project. I'm just going to pick a random BIOS, and that's what happens when you pick random BIOSes. We'll see whether it works though. Nope. I think the X1 works. No. All right. So I'm going to zoom in so that things will actually be visible to you. But all right, this is some examples of what kind of stuff we see down at the BIOS level. Just if I'm an attacker or I'm a defender, wait, which one is my zoom? There we go. Sorry for the pixelation, but there's our Dixie main, so that's going to be the first code that actually executes. And then we have things like system runtime Dixie, system error log Dixie, flash verify SMM. Okay, if I'm an attacker and I want to subvert SMM, maybe if I subvert the flash verify SMM, I'm going to, just for free, be able to get in there. CMOS access from SMM, CMOS access from Dixie, system variable from SMM, monotonic counters. So basically, if I'm an attacker, I go through here and I say, okay, what am I trying to attack today? USB, network access, keyboard controller, and I just have these nice, well-named, human-readable names where I can sort of get a shortcut to access whatever I want to compromise. But this works for us as defenders because when we go out and we, slice this BIOS apart, do hashing on each of these for my clean version and my dirty version, I can tell you specifically that, you had a modification in here. I can pull out the specific portable executable file, and then I can parse its headers, and I can get additional information. So, as I expected, I'd be going long, but a couple last things. Subzero.io, I'm not even going to bother full screening it in because I feel like it's going to crash. Subzero.io is a website where Ted Reed has taken his UEFI firmware parser and he's made it. I like this sometimes when I'm on a machine where I don't want to install all the Python prerequisites and get everything compiled. I just like throw something into subzero.io and then it'll actually parse the BIOS. It'll pull out some of the metadata. And as of a couple days ago, he's also started taking the MITRE Copernicus output about whether or not your BIOS is vulnerable, and he's put that up there as well. So basically, we're starting to work with him on the site, and it's going to be basically a way to crowdsource a determination of, okay, well, if 100 different people have submitted a, Lenovo X1 Carbon at BIOS revision 2.56, then we can say, well, 99 of those guys said that the hash for this particular thing was this particular value, but one person is an outlier and one person has a different hash than everybody else. And so we can start, pulling some notion of what's good and what's bad. So you can go check out that site, subzero.io. It has the ability to do Copernicus reports up there as well. In the next day or two, we'll be rebundling Copernicus with a little script where you run Copernicus, it dumps your BIOS, it tells you, you're vulnerable or you're not. But you can also just hit a little script and it'll submit it up so that we can start getting that crowdsourced notion of BIOS clean or not. What Subzero.io can't do right now is the biosdiff.py, which comes with Copernicus, the actual integrity checking of here's a clean version, here's a dirty version. So you still have to do that manually. And I figured I wouldn't have enough time for this, but if you go grab the slides later, you can look at a 15-minute video where I'm sort of going through the process and saying, here's my clean version, here's my dirty version, run biosdiff, hey, there's a change, let me look at the raw change in bytes, let me pull the two PE files, put them into IDA, analyze them, and most importantly, use those data structures that exist and are already well understood from the UEFI spec. Very, very nice capability within IDA to import header files, just standard C header files, and then apply those data structures to the BIOS, and then that makes it so that when you use hex arrays in order to decompile stuff, it makes for very human-readable code for some value of human-readable. So, in conclusion, I'll let you decide who the angel is and who the victim is here, but the angel said unto him, UEFI said unto him, stop hitting yourself, stop hitting yourself. So, UEFI brings improvements for boot time security so that you have some ability architecturally to actually get rid of these boot level attackers who are just completely subverting operating systems otherwise. And Copernicus has made it so that we have a tool now, it's freely available, you can just go out and download it, run it. You can start having some notion of whether or not your system is vulnerable, because for many years people would do BIOS attack talks and they'd say, well, SMM is vulnerable if this bit is not set. And then you'd ask them, well, are you going to release a tool that checks that bit so like I know whether I'm vulnerable or not? And they say, no, that's so easy, you just do it yourself. Well, Copernicus now has combined all of the information that is currently known about BIOS vulnerabilities, whether they're exploitable vulnerabilities or whether they're just misconfigurations, and it gives us this ability to dump the BIOS, compare it against other things. So we now actually have this nice standardized way. If we tried to do this for the legacy BIOSes, we would run into this whole quagmire of how do we decompress all of the random formats. So that's why it only supports UEFI and newer stuff for now. And that's going to be it. So with that, I'll take any questions out to the side afterwards, let people get set up for the next speaker. I saw the next talk earlier, so I think you should check out Rafal's talk next. But anyone else, you're free to go. Thanks.